started out life as an engineer. He comes from the Frio area, Bond's got little creatures and the dockers and a lot of wind.
Yeah, and yeah. I wish I had more to add, yeah.
Started out as a statistically minded engineer, and then went to a postdoc in Leeds, did paleoglaciology, and he's really interested in spatio-temporal stuff. He was hired here in the spatial statistics cluster. We have a cluster of spatial statisticians in the stats department, and he's going to teach us all about Kriging.
Cool, thank you for that. So, thank you, as David said. So I'm Lachlan. And so, yeah, I'm going to talk about Kriging today, but just quickly on that spatial statistics cluster. So we're calling ourselves STREAM, which is spatio-temporal research for environmental and applied modelling. So I would broadly, when at a conference, brand myself as an environmental statistician, but kind of there's very much the ecology way of thinking about that, which David does a lot of research in. And effectively, the things that I'm interested in is if you can write down the quantity in a PDE, so if that exists in Navier-Stokes or something like that, pressure, temperature, humidity, precipitation, things like that, I'm interested in modelling physical processes in space and time. So that's very much my research. But today we're going to talk about Kriging. I'm kind of just going to discuss this in the spatial setting, although we can discuss it in many different ways. Just so I can gauge the room, who's heard of Kriging before? Okay, half of us. Who's done it? Slightly less, okay. Anyone heard of Gaussian processes but not heard of Kriging? Yeah, okay, so the same people. Okay, so we've kind of got a split room now. So what I'm going to do, I'm just going to go a bit of a zero to hero on the history of this and kind of explain where the Kriging equations comes from and why, and there's a bit of code and stuff. Please feel free to interrupt me halfway through if you want to know more information. I do a lot of this type of stuff, so especially if you've just got weird esoteric questions, very happy to field them. So we'll get started. So 1951. Is anyone here Dutch? Anyone here want to have a shot at that? Hey. We'll stick with that. Yeah. Yeah, Wit Vadersan is my attempt at that. German, Dutch, Afrikaans, maybe we would have a better shot. Okay, this is one of the biggest gold fields in South Africa, okay? So at the time was the world's richest known gold deposit. I think the statistic is something like 50% of the world's gold that's currently in jewelry in circulation comes from South Africa, so very rich gold country. And the question with all mining resource questions or resources questions is where's the gold or where's the asset? Okay, so we've got this big gold seam. So this is a picture of a map from 1902. So it's been in operation for a while. We're trying to find where the gold is. Okay, so we have a bunch of boreholes. So the problem with geostatistics is that atmosphere you can kind of look up. You can see a lot of atmospheric stuff, and we have satellites and we have radars and things like that. Ground's a lot more opaque, okay? It's quite hard to infer what's happening through the ground. And so this is still very much a problem in geological engineering. And so we have a bunch of bore sites that we've drilled, and so these are our coloured dots here. And the question is, well, where do we want to go next? Each one of these operations is expensive, and we're trying to find where we want to drill next, where we want to put those resources and that allocation. So this is the question. This is the central question for exploration. So can we estimate the grade at an undrilled location, and then can we stake a mining operation on it? Can we back that up with the money? Can we build a business case? Can we do that? And can we quantify our confidence? You know, when we want to make a business case, we can't just say a prediction. We also want to give a degree of confidence to our prediction, okay? So this is So this is, I guess, the problem here, okay? So we have like a mining block that we want to look at. We have a local estimate, so maybe we've taken stuff around it, or maybe we have some covariates, maybe we have, you know, different measurement campaigns. We have an estimate of this problem, but the problem is that the high estimates are often too high and the low estimates are often too low, okay? And so this essentially starts to be described as a spatial regression to the mean, okay? So this is not, for the statisticians in the room, marginally we can be unbiased, but conditionally we can be biased, and this is the problem with spatial estimation and Kriging. If that sentence made no sense to you, it's fine. We can continue without it. Okay, so But essentially, when we're sampling in random locations, extreme estimates are partly from geology. So in an estimate where we get a higher sample, that's partly because there is a large reservoir there, but there's also noise, okay? So we might have also been lucky on top of a high reservoir. And so this is kind of what I mean with this spatial regression to the mean, okay? So that the noise will inflate the extremes, and we kind of want to be taking a spatial structure and looking in the middle of that. So this is what Danie Krige, I'll call him Danie because then I don't have to worry about if there's an L on the end of his name or not, depending on the language that the documents have been written in, that L appears or disappears. So we'll call him Danie Krige because we're in Australia and we can make up people's names. So mining engineer, and at the time was a part-time master's student, okay? And when I was pulling some of this together, there was lots of obituaries that I found on the internet randomly. Sounded like a nice guy. Okay, I think that's important context. And so in 1951, in this year that we're talking about, so he's 32 at the moment, doing a little bit of research, mainly being an engineer. So he published a master's thesis, and this kind of led to this notion in this field of Kriging. And it was called a statistical approach to some mine valuation and allied problems on Witwatersrand. And very much that observation that we made earlier is what he was talking about, is that our extremes are often too extreme, and we seem to be losing a little bit of information when we're making these estimates. Okay, so if we take our development estimate, so all these measurements and stuff that we take, and we're trying to estimate what our eventual mine value is, okay? So if our estimate is this V hat, and we have the expectation of what the actual V ended up being once we mined that location conditioned on a V hat, if everything's perfectly unbiased and everything's predicting well, that B should just be 1, okay? Our estimate is giving us our eventuality. And what Krige realised is that it did a big empirical analysis of all the, the estimates and these locations, and effectively found that that B is less than 1. Okay, and this is a mathematical realisation of this notion of a regression to the mean. So then what he did is what he did in his thesis was estimate a B. Okay, and so essentially it's a discount factor on the extreme. So the high estimates are high, but we pull them down a bit. Low estimates are low, we just pull them up a bit. Okay, and so this was the insight. Took a bunch of empirical data and said, don't just take our prediction, let's calibrate our predictions. Okay, so for anyone that's done Kriging, this looks nothing like Kriging at the moment. So this is a bit of a weird stage left into the problem. But this notion of near things are more similar and a spatial regression to the mean and conditional bias, and it's very much everyone's circling this same notion in the solution, which is the Kriging solution, which Tobler summarised in his Laws of Geography paper, which is that everything is related to everything else, but near things are more related than distant things. Okay, so this is very much on the back of what Ben was talking about as well, is that we have dependencies. Okay. When we take measurements of things, the world is not IID, the world is not normal. Central limit theorem is convenience, but often is not the reality, okay? And so in our problem in mining, if we're in an ore-rich area, we would expect to go find more ore around there, okay? Weather, we have correlations, all right? If I go 10 k's down the road versus 1,000 k's down the road, it's going to be very different climates, conditioned on what we're looking at here, okay? Conditioned on that we can make some observation here. Property, houses on the same street have similar prices, and medicines, so clustering of disease rates, okay? Often through confounding variables or what have you, but there are clusters of diseases. Now, the point is that spatial coherence isn't just interesting. It's not just like a thing that we can look at. We can actually exploit that too, okay? So if I want to know what the temperature in Central is at the moment, I have a much better shot at guessing that from sitting here than sitting out in the Blue Mountains, okay? So we can exploit this notion of distance and we can exploit this spatial structure to actually tell us something. Now, this actual mathematical foundations is what Krige measured, but it's not what he did, okay? So it's just what he measured. So Matheron, about 10 years later, came along and formalised this into what we know now as Kriging, okay? Is anyone French? Nope. Do you want to have a French shot at the name, David?
Georges Matheron.
Perfect. I'm still on probation, so I don't want a HR incident. So I'm farming this out to the professors. Okay. So George, again, we'll make it Australian. Georges Matheron, so he read this work and took this idea, this very empirical idea that Krige had come up with, and he formalised it. But he formalised it in the question that in today's parlance and as a group of statisticians, or at least statistically curious, this would be probably a little bit more familiar than how Krige approached the problem, is that if we take all of the data that we have, okay, and we want to build some sort of estimate from that data, okay, so we want to take all these observations and we want to put that into a function, and we want a prediction, okay? Of all the possible weighted averages, what has the smallest error? That sounds pretty good, okay? We want to take all the data in a way, we want to make a prediction that minimises some error criteria, okay? And can we derive it? And over that following decade, so this was his first paper was in 1962, and so until the early 70s, kind of built this notion of Kriging, which he named in Krige's honours. And this is also very much like the birthplace of geostatistics as it's familiar today. So statistics has always been tied to a notion of space and time in the environment. So back to Fisher's work in the 20s, I mean, Fisher made that very similar observation to Tobler, where crops in neighbouring fields are more likely to perform better, okay? But this modern notion of geostatistics and the equations and how we interact it today, very much built on Matheron's work here. Okay, so how do we do it? Okay, what are the mechanisms that we're going to use to actually build up this framework? Okay, so that's a little bit of the history, and now I just want to go through a gentle and then a very one-slide quick way through Kriging, and then we'll look at some nice pictures. So first we need a number. First we need to map empiricism into something objective, okay? And say we have a distance h, okay, between what we're measuring and what we're wanting to predict, and we'll call that distance h. So on average, how different are values at two locations separated by h? So this is the variogram. So who's heard of a variogram? Slightly more people than have done Kriging, okay? So the variogram has ended up being useful in lots of statistics, okay? So this is one of the main tools by which we characterise dependence. It's essentially also an empirical autocorrelation function. You just flip it around a little bit differently, but it is effectively a one-to-one map of those two things. So in 2026, we'll tend to talk correlation functions or covariance functions. Back in the day, or if you go into engineering, they will still likely talk variograms. But what it is we have this little gamma, okay? We have this distant h that we're talking, and we have a location s, and s is where we are in space, okay? So if we take our measurement at a point s, we take a measurement at a point s plus h, what's the variance between those two quantities? Okay, now intuitively, if I know exactly what's happening at point s, something very close to me should have a smaller variance, okay? Because it is in some notion pinned by what I know here. And as h gets big, we tend to independence, okay? What I know here has nothing to do with what I know over there. So this is the tool that Matheron built and on which kind of, you know, all the science is based. So this is what a variogram looks like. I've just made this up. This is from a squared exponential, if those words make sense. So there's three things that a variogram has. So there's a range, there's a nugget, there's a sill. So the nugget is effectively observation error, okay? So that's saying that if I know something here and I go an infinitesimal distance, okay, there's going to be some notion of variance, okay? And that can just be, that can be measurement noise, for example. It can be a few other things, but effectively we think of that nugget as a measurement error term. We have a range, so that's the distance h over which a notion of correlation makes sense. As h goes to infinity, we're going to go to independence, and there is a practical notion you know, at a distance h away that we just don't care about the dependence anymore. It's just too hard to deal with. And then there's a sill, okay, which is essentially the scale of the problem. Okay, we need some sort of scale. Now, if we take all of our data, okay, and we bin the pairs, so we take, I think I've used 300 data points here. This is all empirical. I just made up this problem so I can make some nice plots. But I took 300 data points. I take all the pairs of the observations, so that's 300 squared, and then I plot the distance. I plot, not the distance, the difference between them with the distance on x, and then I wrap that, I square it, and I wrap it in an expectation. We get it variance, okay? So this is very much an empirical thing. So these faint dots in the background are all the pairwise things. It's messy, okay? Squares are messy, so they're everywhere. But if I take what these bigger points are is some binned average, okay? So I've taken every 1 on 3 h, and I've just binned all those things, and we can see on average, so this is that notion of an expectation, on average we're trending to this variogram. What I'm not going to talk about in this, because this is a whole area of research, is how we fit a variogram, how we come up with that families we use, things like that. In practice, and certainly in the 70s, this was very empirical, very similar to what we're doing here. Take all your pairwise, you plot them, you put a smooth line through them, you get on with your day. And for the purposes of this, we can just assume that's what we're going to do. Now, the shape of our variogram tells our story, okay? This is telling us this notion of spatial dependence. So if we have a steep rise, so very quickly this is going up, we have a short-range correlation. So our spatial dependence isn't as exploitable, okay? We're tending to independence more quickly in H. If we have a gradual rise, we've got that opposite. We have a very smoothly varying dependent field over longer scales. And if it's nugget only, if we're not getting any structure there, that's when we're kind of in this independence regime, okay? That we have no dependency structure to exploit. Right, so one word and the terminology that Matheron used when he wrote this down in the English version, anyway. David can have a go at translating this into French, but we'll see, is that we want a weighted average, okay, a weighted linear average. So our points are on the right-hand side here, so that those SI are where we've seen things, okay? We want a weighted linear average, so we have all of our lambdas there, okay? And we want to make some prediction, some SO, which is just some other SO, some other location in space, okay? And so what we want is the best linear unbiased predictor, okay? So this is a term that's used outside of Kriging as well. This is a term used a lot in statistics. But we want to solve for the lambdas such that we get the best linear unbiased predictor, which if we unpack that as a term, as a terminology that we might use, predictor, okay, I mean, fairly self-explanatory, we want a number, okay? We want it to give us something, and we want, so it's essentially a guess at S0, okay? That's what we're looking for. Linear, it's a weighted linear sum, okay? So this is this structure that we have up here. So we don't have a magical F, we don't have a neural network, we don't have anything wonky going on, and we can guess because we're linear, we're in a safe space, okay? We can do stuff. Unbiased, okay, we don't want to be systematically wrong, okay? If I take the expectation on the left, it should equal the expectation on the right, all right? So that actually gives us the constraint that the sum of those lambdas should be 1. That's just like a esoteric side note. But we just want to know that these expectations are equal on the left and the right. And then the best, okay? So we need to define our family of what could come from. And again, so the family is this form that we have on the top, such that the sum of those lambdas equals 1, and that's giving us unbiasedness. And we want to minimize the mean squared error. So we want to set up an optimization target, we want to do a minimization. Take the derivative, set it to 0, and we're good to go, all right? So this is my one slide of maths, and then we're going to get to pictures, okay? So this is what we set up. So we have our weighted average on top. We want to estimate our lambda, okay? We set up a optimization target. So that's the mean squared error over there, that we want the expected squared error to be minimized, all right? So we're going to set up that optimization target, and we're going to minimize that. Now, I've made a jump from the middle equation to the right equation. There's a bunch of C's that appeared, okay? Now, those C's, they're just values we're reading off the variogram, okay? So this is how our spatial structure enters these equations, is in the optimization. Now, if you just interested in a good Friday night, you can go home, you can expand that square, you can roll the expectation through it, you can see where variances pop out and where they don't, and you've got squareds and expectations, you're going to get variances, okay? I would suggest a glass of wine instead of doing that, but you can. But But what these C's are is essentially where space is coming into it, where this notion of spatial dependence is operating. Now, we minimize that, okay? So we minimize that, we get an estimator, we get a lambda hat, we plug it back in to that weighted sum up there, and we get our prediction, okay? So all it is our data, this cap Z here, that we've stacked into some vector, okay? It's an inverse covariance matrix, okay? And then it's something, this CO, that's mapping it to our location in space. We can also, if we take that and we put it into the variance form, we can then also get uncertainty. So uncertainty ships for free. This is actually just the value. Once we have these lambdas, we can just wrap that in a variance, and it all drops out because it's linear, okay? Now, has anyone seen equations that look like that before? Jake, do you want to volunteer where? No? Okay. That's the Gaussian update, okay? That's when you condition a Gaussian distribution. That's exactly what that looks like, except we've kind of played some silly buggers with the variance matrices, okay? So if you've done any sort of Bayesian 101, this is where, you know, your posterior distribution of a normal parameter given normal observations. That's exactly that form. If you've done Kalman filtering, this is what this looks like. These equations are ubiquitous. They pop out everywhere, okay? And how they're working for us now is that we've just got this variogram that's informing these certain correlation matrices that we have in the middle. Cool. So that's all the maths. We'll make some nice pictures now, okay? So I'll kind of take everyone through just a little, you know, like how we might use this in practice. I've written it in R because I figured stats happens in R. This all happens in Python. There's very mature stacks in both languages. MATLAB, if you unfortunately operate in there, got to help you, but this is in R. All these slides will be online, so if you want to copy-paste code and things like that, you can as well. But if we want to generate, okay, what I've done here is I've generated a random field, okay? I'm going to take some observations and we're going to try and predict that backwards, okay? So we have some notion of ground truth here. This isn't, you know, quote-unquote real data. This is simulated that we know. So how have I done this? I've defined this simulate field function here, okay? So, which I've copied that function up there. When you're doing code, put stuff in functions. It makes code nice and readable. So what we're doing here is we're saying, do I have a laser pointer? Oh, yeah. Can you see that? No. All right. What we're doing here is we're defining a grid, okay? So we're taking a grid at some resolution n over 0 to 10, and we're defining a grid. This expand grid gives us all the pairwise grid values there. We're turning that into a matrix, and we're turning that into a distance matrix. So what D does is it gives us all the pairwise distances in Euclidean distance between every location on our grid, okay? We're wrapping that in this function called covx, which is standing for the exponential covariance function. That's the parameterization, or that's like a parametric form to that variogram that we were showing before. So we've got D, which is representing our distance. So that's the difference in h's, so that's the x values on our variograms. Then we have something mapping that to the y values of the variograms. We add a little term here because if you invert matrices that are very, very smooth or very close to positive semi-definite rather than just positive definite, inversions can be a little bit finicky. So what you'll see a lot if you're doing this, people will talk about jitter or a nugget or things like that. That's often just like a very small diagonal you add to your matrix, which makes it stable, okay? If you haven't seen that terminology before, it's actually not many people talk about it when they're posting. Everyone has ChatGPT these days. It'll just tell you. 10 years ago, it was tricky. It wasn't tricky, it was just opaque, okay? And then we're generating a sample, okay? How we're doing this is a little bit of a gross way. This is, you know, a computationally stable way. You can do a mean Cholesky transformation of 0, 1 IID data. Esoteric. We're taking a big draw from a normal. Okay, that's all that's happened there. And this is what the field looks like. So this is the background colors is just some random spatial field that I've generated. And then our observations, which are here, I've just taken 40 samples, random samples from that, okay? Now, if I take just those observations that I pretend to have only, and there's some error in that, okay? I've taken, just IID error on top of that as well, which is where you get this kind of like splotchiness from. So if I pretend like I've only seen those observations now, and I try and estimate it back, okay? So I'm going to go through that Kriging prediction equation. So I've got my big C, okay? So that big C matrix is now essentially, it's that same thing. It's a distance matrix on the observation. So it's the pairwise distances of all the observations. We wrap that in the covariance or variogram function. That's just a big C. Our little CO is just the same thing, but it's just mapping all of those locations just to SO, just to the point that we want to get at, okay? We roll it through this equation here, okay, which is just the prediction equation we had. It's a CO times a matrix inverse times all of our data, okay? If you plot this prediction, this is what we get on the right, okay? So a nice kind of smoothed out prediction that's spatially coherent in some way. This variance formula I've just put up here because there's no point, it's one line, there's no point repeating it other sides. We're going to plot that variance term in a sec, but that's that second equation that we had, okay? So if we compare, so our true field on the left to our predicted field on the right, you can kind of like, if you squint your eyes, it looks nice, okay? So there's some measurement error that I've artificially added in on the left-hand side, which we're never going to get error, okay? We're never going to model error, and we shouldn't, That's not something to be modeled. But you can see, this high spot here is also high here. We're getting this very broad trend that's coming through this Kriging equation as well. So that's nice. We can look at the error of that. So if I take the difference between these two fields, this is what I'm showing on the left here. And what you can probably see is that the most extreme bits that we have error, so the dark greens and the dark reds, that's happening between the observations, okay? So down here we don't have many observations, so we have over-predicted where it's green, under-predicted where it's red. Big dark red spot here where we don't have observations, big dark red spot up there where we don't have observations, okay? And if we look at the variance map on the right-hand side, so this is just the diagonal of that variance term, so we're looking at the marginal variance here. You can see what Kriging is doing is it's saying we're pretty confident where we've seen data, and the further we get away from our data, the less confident we're getting, okay? And that's exactly this notion that we've been trying to build up. So these are just nice, pretty equations, but this is so there's a reason why nearly 60 odd years later, this is just still very much in a spatial statistician's workflow and stack, okay? These are really powerful tools. Any questions kind of on the application or the use case? No? Oh, yeah.
Is there any assumption or requirement about the sampling points to be random?
No.
If you did it like in a two-stage process where you predicted and then sampled high predictions.
Exactly. So the nice thing is that our variance, okay, is actually independent of the data that we see. So if you think about, I'll show you the equation. We'll bring that back up. So there's no Z here, okay? So we know, conditioned on a variogram or a covariance function, we know exactly what our updated or conditional variance is going to be. So typically what you do is you actually would never sample randomly. In practice, you'll do something intelligent to try and minimize the variance of whatever you're targeting. Are you targeting a point? Are you targeting a region? Are you targeting a whole area? That decision is very much like use case specific, but you would design where your points are to minimize the variance of whatever you're trying to target typically, okay? Now, two-stage things all the time, okay? So in science, very rarely experiments just a one and done type thing. So you do something, you take that information, you put it into some sort of conditional update, and then again, you design the next round of points to say where do we need to go sample to learn the next wave of stuff. Absolutely, yeah. Cool. Anything else while we have pictures up? Yep.
Where does the term nugget come from and why nugget?
Couldn't tell you. So I don't actually know. So it's probably more, no, people use nugget a lot. I'm not sure. I don't know. Yeah. It's also called jitter. Jitter makes sense. Okay. Jitter is the jitter of the true field. I don't know. I want to say like it feels mining related, but yeah, I'm not sure.
Expect it to be this big, but then you get a great big nugget.
Maybe, yeah. I think wildly speculating is actually the right answer here. Yeah. Sorry? Sill? Because it's kind of like it's a ceiling, right? So it's the ceiling of the size of the effect that we're looking at. Yeah, yeah. Ceiling. Yeah. Really like interesting and murky question. Yeah. Yes and no, which is like not the nicest answer. So often in science, you're making a set of scientific assumptions. Okay, and so in any statistical model, there are, whether you're explicit about it or not, there is a whole line of assumptions baked into it. So your ability to take somewhere where you've observed nothing and say, well, it's just going to behave the same as this neighbouring one, is often predicated on some sort of, there is a geologist or something like that is saying, is this assumption okay or not, or if not, how wrong is it? And so a lot of the time, yes. So like a lot of the time we will understand. So mining is actually a really tricky example because when you have geological formation, you have really rapid rock changes, okay? So it might just like suddenly no more gold. It's just ended, okay? So it's really hard to transport. Things like atmospheric science, forests, things like that are following a bit more of a continuous physical relationship. It's a lot more feasible to kind of plug and play the methods across those, but it's very much predicated in the science. Yeah. Good, really good question.
But even if like the variagram did transfer, you've still got no data here, right?
Oh yeah, you still have no data. So like but you could design your experiment condition on a variogram, maybe. But yeah, if you also don't have any data where you've observed, you're not getting anything predictively informative just yet. But it might inform you how to do a sampling procedure or an experimental design. Yeah.
Microbiology
Mm-hmm.
or related. So just wondering how is that going to, if this applies well
Mm-hmm.
when we're sampling for bacteria from like population in one area versus the other, 3 different cities, or if there's way too much factors for that to apply this model?
How long's a pizza string? Yeah. How many? So you can. There are again. There's 50 years of work built on top of this, right? So you can add nonlinear means onto it, or you can add other scientific models and use this to model like a spatial residual. You can also wrap this kind of similar to what Ben was saying in a generalized linear model framework. So in that assumption where we had the weighted sum, that's just a linear model. So this is just a very flexible version of the generalized linear model. So even if your response variables aren't continuous or not, you can still use this at some level to model a mean structure. I don't want to just say like yes or no because I need to understand more context, but there's a very mature pipeline of tools that can be built on top of this. If you're interested, please send me an email. Happy to talk about it further. Yeah. Mm-hmm.
You expect to sample more in one area than other, whereas I guess from a homogeneous landscape, you probably get away with sampling more evenly. Is that a correct interpretation?
Yeah, so in that there's kind of a sneaky notion of stationarity. So I've kind of skirted around that idea of when you've got homogeneity versus heterogeneity. you homogenate. We're kind of implicitly assuming some notion of stationarity here. With your sampling, something like this, so when you have a homogenate, like a constant field, or we have these assumptions, a really good start point is people do something called a Lachlan hypercube sample, where it's not, grids are really inefficient for space filling, okay? Like just designing all your points in a grid is a really inefficient way to go about sampling. So what Lachlan hypercube sampling does is it operates to minimize the sum of the distances between all of the points, okay? So it is a maximally space filling design. So if what your goal is to understand a whole region, that's probably what you would do. If you know that you have heterogeneity and you have regions that vary faster than otherwise, you would probably oversample in those regions. But again, we're starting to get beyond what was being done in the 60s and very much that type of work, that type of warping work's kind of like the 2010s, but there's definitely things to do in that field. So I'm going to wrap up quickly, and then if there's time at the end, we'll take more questions. These last points are just a sequence of points that mainly are just anyone that's taking these slides home. I just wanted there for posterity, but we don't need to spend much time on. We have a prediction surface, we have a variance surface, okay? So our prediction is smooth if the variogram set it smooth. When we go far away from the data, it's going to regress to some notion of a global mean, and it's passing through our observations, okay? And then the variance, as we said, it's kind of like it's getting pinched in on our observations. We have very little variance. Where we've seen things, we have lots of variance away from data, okay? And again, this point here that I've been talking about is that our variance depends on our sampling configuration, not the values that we see, okay, which is quite a powerful concept in sampling design. We can construct intervals, okay? So we can take, at a point, we can take our variance, we can times it by, depending on how confident we want our intervals to be. We can add that onto the prediction. There is a sneaky assumption of Gaussianity in here. So one thing that I don't know if anyone's noticed, we haven't made a probability assumption yet, okay? At no point did I say the data are Gaussian or the data are T or the data are anything. All of this comes just from the first-second moments, just from having an expectation of a variance. To do other things, a lot of the times we'll put a probability model on it, but this is one of the really cool things with Kriging is that it's kind of invariant to the choice of a probability family, which is a nice property of it. There's a whole family. Okay, there are decades worth of this stuff. There is an incredible textbook, Noel Cressy's book, 1993, which covers a lot of that, obviously, up until 1993. And this Kriging has very much turned into what machine learning would now call Gaussian processes. So if you see Gaussian processes in the machine learning literature, this is where a lot of this comes from. So there's a few basic variants, okay? Here are some funkier variants that we don't really need to go in, but they definitely exist. And this is also what I wanted to do, to kind of touch on, is that these notions and these equations are everywhere. Once you have that updating equation baked into your head, you see it in Bayes statistics all the time. You see it in GP regression in machine learning that I've been talking about. Kalman filtering, any engineers do Kalman filtering? Kalman filtering is a special form of Kriging, okay, with a special variogram structure. Same with signal processing, and then Bayes linear. So this is this kind of notion that I was talking about before. We haven't assumed a probability model yet, so you can still do statistics without probability, which is weird. My first postdoc was very much in the heartland of Bayes linear statistics, so I have lots of things to say about it. If anyone's interested, buy me a beer and I can rant about it. We don't need to go into packages. There's heaps of them, okay? These slides will be online. If you want to interact with this stuff, Kriging has a very, very mature stack of packages, and there's always more stuff and more flexible stuff coming out. Things that I've ignored, things that we'll continue to ignore, okay? Thank you so much. So slides, I'll put them up on my website. Please check Stream out. I think we all do really fantastic work, and if you are a scientist and have things that vary in space and time or environmentally, please raise your hand and talk to us. It'd be really great to work with more people at UNSW. And that's my email if you want to get me. Thank you.
Merci beaucoup, Willem. Any questions?
Bitteschön.
Are there any physics-based models for this kind of problem?
Yeah, is this like... I just released this paper 2 days ago, which is doing physics-based Kriging. So this isn't like, this is just, I didn't plant this question. This is just my own document that I had open that I've been working on. Thank you. I'll pay you off later, yeah. Physics-inspired GPs, where you're kind of saying that our latent field also adheres to some GP or some process. There's been lots of iterations on that. So if it's a linear PDE, you can do it exactly, okay? If it's a non-linear PDE with anything non-linear, you're in a world of hurt. We have this very cool paper that is on arXiv as of 2 days ago, where we're saying on your left-hand side, this is what your kind of classic Kriging estimators would give you, where you have no notion of physics. Whereas if we also constrained our estimates to give us physical adherence, we get these really beautiful things. So,
How computationally heavy?
Not too bad.
Not too bad.
It's actually so. Typically, don't need a GPU. Huge data, huge problems need a GPU, but this method's very parallelizable as well, so you can run it over many cores. We can talk offline. This is like new esoteric maths, but yeah. Buy you beer later. Thanks for that question. Allowed me for a plug. Do we have time, or we're done, or where are we up to? Maybe one more question? Or not?